Hi students, Mr. Danahauer here. Today we're going to be talking about relative dating. This is a process where we can date rock layers according to where other rock layers are. So the first thing we want to talk about with this is to understand the different types of rocks. Hopefully you remember from some point in your education that there are three main types of rocks. Igneous rocks, which form when molten magma or lava cools and hardens. So we get examples like granite, which we see a lot of in Colorado, obsidian, scoria, and pumice. These are all different examples of igneous rocks that come from molten magma or lava. The second type is sedimentary rocks, and sedimentary rocks are formed from broken down other rocks, right? So we get sediment that forms from the process of weathering, and we form other rocks when those get cemented together and solidify into a rock layer. And so we see examples, lots of examples of that in Colorado. We have sandstones. As we get farther out into the eastern plains, we see a lot of limestones, and we do have some limestone here in Colorado as well. Lots of other examples of those. The last is going to be a metamorphic rock. Metamorphic rocks comes from existing rocks that are changed by heat and pressure. And so again, in Colorado, we see a lot of gneiss, Gneiss, because we have a lot of granite here, and we've also had a lot of extra pressure from plates moving around, and that's formed that changed that granite into gneiss. We also see a lot of quartzite in Colorado. Other examples are marble and slate. So we'll keep moving on here. That brings up the rock cycle. Where do all these rocks come from, and how do they move from one to another? The first we can see here at the Earth's surface, if we have magma in the center of the Earth, right, and that comes up, but it doesn't reach the surface and it cools underneath the surface, it's going to cool slowly. And so we call that an intrusive igneous rock. It's cooling inside of the Earth. And those are usually, those igneous rocks usually have big crystals because the slower an igneous rock cools, the bigger the crystals form, the more time they have to form. If the magma comes to the surface of the Earth and is able to come to the surface, then we're going to have a faster cooling process. Those are called extrusive igneous rocks, and those are often those have very small crystals in them. Whether no matter what kind of rock we have, we can see that those can be on the surface of the Earth at some point, and they can get weathered down. So weathering occurs from things like wind erosion, water erosion, which is very common, ice, freezing and thawing of ice. These all break down rocks into smaller pieces, and we get sediments. Those can get buried, moved, buried, and then solidified into sedimentary rocks. And of course, any of the kinds of rocks can then be exposed to heat and pressure at any point, and that can change them from being an igneous or sedimentary or even a metamorphic rock into a metamorphic rock. This rock cycle just kind of gives us a good picture of some of the processes that are going on to form different types of rocks. Now, we're going to really focus on what we call rock strata, and strata is just like layers. So strata just means layer, and so we're going to look at different layers of rock, and then so we need some symbols so we know what kind of rock we're working with. And these are the geologic rock symbols that are often used. On the top part, we've got sandstone, limestone, down to rock salt, dolomite. Those are the symbols we usually use to show that that's that kind of rock in that strata or layer. And then we get into some metamorphic schist, gneiss up there, and those we often see some wavy lines because a lot of times with metamorphic rock we get foliation or layers and folding. And then if we have little V's and X's, or even just black, usually that's going to be our igneous rocks like basalt and granite and other igneous rocks. Okay. So we're going to see these a lot, and you'll need to refer back to this as we're looking through our different rock layers and trying to date them. So how do we date rocks? Well, first of all, why would we want to date rocks? Um, we really want to get a picture of what's happened on Earth, right, over time. Giving us a picture of how the Earth has formed over time lets us understand the processes that have been involved and what's been here. And that's important to have that historical knowledge for many reasons. And a big reason why is that it also allows us to project what's going to happen in the future, right? If we know how the Earth has changed over time, we can look into the future and predict, well, here's what might happen. And that can benefit us as humans in many different ways. So how do we date rocks? First is relative dating. We use the clues around that rock based on other rocks to determine when that event occurred. So when did this limestone layer get laid down? Well, it's older than this layer, but it's younger than this layer. So all of the dating here and relative dating that we're talking about today, we're not putting actual numbers or dates on the age of things. We are just saying, compared to other rocks, this is older, this is younger. And then the other type of layering or dating rocks is absolute dating, and that's where we actually do radiometric dating with radioisotopes, and we do some calculations. There's a lot of sophisticated math in that, and it allows us to put actual dates onto rocks. So we're going to look at some laws or principles today to better understand how scientists do relative dating. What principles are used to date things? Now remember, laws and principles kind of describe how things happen in nature. How does stuff happen? And so all of these are laws or principles because they describe in general how these layers or strata are laid down or how they move and that kind of thing. So the first one is very simple. The principle of original horizontality. Horizontal means flat. We know that sedimentary rocks and igneous rocks, if they are coming to the surface, that because of gravity, they are going to be pulled down and they're going to lay down flat. That is a principle that is true throughout the earth. We know any layer that we see is going to be laid down flat. If any kind of faulting or tilting happened or folding, to change them and those layers are no longer horizontal like you can see in the picture with the car in it, those layers got tilted up. Well, we know that they were originally laid down flat because the principle of original horizontality tells us that layers are laid down flat. And so the layers are older than the event that caused them to tilt up and be tilted up in that direction. We don't get layers laid down sideways like that. That's not how it works. So principle of original horizontality says layers are laid down flat, and anything that is tilted, that tilting or folding event had to happen after those layers were there. So that event would be younger than the layers that actually got tilted or folded. The next one is the law of superposition. So superposition just refers to a very simple idea that in multiple layers of rock, our oldest rocks are going to be on the bottom and our youngest rocks are going to be on top. That makes sense, right? This is not anything that's mind-blowing here. As sediments get laid down or lava comes out or whatever, they get laid down one on top of the other. So we get an older layer on the bottom, and as we go more towards the surface, we're going to get younger and younger. Now there are times when rocks get folded completely over, and we end up getting this out of order. And so we have to just not look at the the strata that we're looking at. We may have to look at a lot of other strata around this area to know that. But in general, oldest rocks on the bottom, youngest rocks on the top. The next is called cross-cutting relationships. And so and the principle of cross-cutting relationships says that if there is anything that cuts through a layer of rock, and by that I mean two different things. One would be an intrusion, where an igneous rock like magma pushes its way into other layers of rock. This happens all the time. If that happens, what this is saying is that that magma, that igneous rock that's cutting through all the other layers must be younger than the layers that it cuts through. The same thing with a fault. You can see in my picture, I have a line that kind of cuts through here. It cuts through a bunch of layers of rock. And so because of cross-cutting relationships, we know that all of the rocks that fault cuts through, they were there. They're older than that fault. We can also use this to order when did C happen, that's an igneous intrusion, compared to when fault B happened. Well, C cuts through B. So we know B, the fault B, had to be there before it's older than event C, which was the intrusion with the igneous rock pushing its way in. So again, we can use the principle of cross-cutting relationships, and it says that anything that cuts through any layers of rock or faults or anything else is newer, younger than what it actually cuts through. Just real quick, what is a fault? That's when we have chunks of Earth that move across each other. So our crust is actually, or lithosphere is actually either dropping on one side or lifting on another. We can see that like with a normal fault, or it could actually move parallel to each other, sort of like a transverse fault. So there's a couple of a transform fault. We could see different types of faults. And so again, we would look at a fault on a diagram and say, oh, because of cross-cutting relationships, I know this fault happened after this rock or before this rock. Also, with cross-cutting relationships, there's different kinds of intrusions. As you can see from my picture here, there's a magma chamber, that red magma chamber, and that's pushing its way up through all of the existing rock that's already there. And so those have different names. A large plume of magma is often called a batholith. If it moves off to the side, it's called a sill, and if it moves in an upward direction, it's called a dike. And so there's lots of different names for these, which you don't need to worry about the names of them, but you just need to understand there are lots of different ways that magma can push its way up and then solidify and cool and form igneous rock. Okay, the next is the principle of inclusions. An inclusion is a chunk of rock that's found inside of another rock. So for example, in my picture here, if I had this purple layer, let me put my pointer on here. If I put this purple layer here, and there just happened to be a lava flow and a chunk of this purple broke off and it's in the lava flow, that would be called an inclusion. Also known as a xenolith or strange rock because it's foreign, it's not the same material that it's of the rock that it's in. So we often see xenoliths or inclusions in other rocks, especially sedimentary rocks that have incorporated other pieces of bigger rock or lava or magma flows where chunks of rock have fallen into that molten rock and then it still exists there. So here's the thing. In order for a chunk of rock to be inside of another rock, the chunk of rock has to have existed. It has to be older than the rock that it's inside of. Right, that makes sense. We can't have a rock and then something just magically forms inside of it later. If there's something in there, that thing had to exist first. And the next topic is the idea of contact metamorphism. So as we mentioned, metamorphism is whenever we have a rock and it's exposed to heat or pressure, and that's going to cause the rock to change. Well, whenever we have an intrusion, like a batholith, a plume of magma that comes in, or any kind of intrusion, that intrusion can actually change the existing rock around it. And so you can see from my picture here, it's kind of wavy lines where the heat and pressure have pushed on that rock that's around there and caused what we call contact metamorphism, where the magma has contacted the existing rock and caused it to change into a metamorphic rock. A lot of times in this boundary, guys, we'll see little stars. Those little stars will indicate that there's contact metamorphism, or you might see little dashes. But if you ever see an intrusion with an igneous rock, and then on the outside edge of that, you see some kind of an indicator like dashes or asterisks, that tells you that there's contact metamorphism there. Okay. What this tells us in terms of relative dating is that the contact metamorphism, the rocks that were metamorphosed or changed, had to be there before the intrusion that caused them to change. So the intrusion is going to be younger, the magma is going to be younger than the rock that it's pushed into and changed. The last concept here is called fossil succession. And so we're not going to really dig into this a whole lot, but one of the ways that we can relatively date rocks is by the fossils we find in them. We have a pretty extensive record of the fossils and when different organisms have existed and when they've gone extinct. And so if we find a certain type of fossil, for example, a mammal fossil of some rodent, and we find that in a rock layer somewhere, we can say, well, this rock must have been here around this time, assuming that we're confident and we can confidently say that that skeleton of that mammal is in fact what we are saying it is. And so there's other techniques for that portion of it, but we can use fossils to date those rocks. We can also use them to categorize or index rocks that are, if we find a rock layer in North America that has a fossil, and then we find another rock layer in Europe that has the same fossil, we can say those probably were formed around the same time period. So fossils are a good way to help us to relatively date rocks. One thing we're going to see in the strata that we look at in the different layers is sometimes we're going to see erosion. So we'll get lots of layers laid down, but then if the environment changes, we might get an erosion event, and these are called disconformities or unconformities, nonconformities. It's where there's not a continuous, there's a break in time where we don't really know what happened. We just know that there was some erosion going on. And you can see the dark line on my picture here, the slide. We have a sandstone layer underneath and a limestone layer on top. At some point, there had to be some erosion. That wavy line that's in there, it's not consistent, the layering. So there had to be some kind of an erosion event that occurred. So maybe we had a beach here, and in this layer of sandstone, there was a beach environment. And so we get a lot of sand building up over time. And then the ocean kind of went away for a while. Maybe we had an ice age and the ocean receded. The water level went down, and through rain and rivers and stuff, we get erosion wearing away that sandstone. And then the ocean comes back, the ice age is over. This is just me hypothesizing what might have happened. The ocean comes back and we get a deep ocean environment, and now being laid down on top of that sandstone are a bunch of marine organisms, shells, which is the result of limestone. That's how we get limestone here. So we see these erosion events happen sometimes. If there's an erosion event, we just know that the layers under the erosion event are older and the layers above it are younger. Okay, so we're going to go through a few examples here, and I'm going to talk through, first of all, how do we order them? How do we know what comes in which order? And we're going to use these laws and principles in order to do this. So you have to pay attention on the questions we ask you. Do we want you to put it in order from oldest to youngest or youngest to oldest? So make sure you pay attention to that. I'm going to go ahead and kind of work backwards. We'll do the oldest layers first, and we'll work our way to the youngest layers here. So in this example here in the picture, you can see I have a limestone layer A, I have a shale, some kind of shale layer B, and a sandstone layer C. I also have an unconformity at F, where we had some kind of an erosion event, and I have a sedimentary layer at E as well. And then I have a fault at D. So we want to sequence these. What's the oldest event or layer in this picture? Well, A, B, and C are the oldest layers, right? They're underneath. And so A would be at the bottom, B is next, and C is next. Which principle did I just use to layer those and say A came first, and then B is not as old, it's like younger, and then C is the youngest of those three rocks. A is the oldest, C is the youngest. Which principle did I use? Well, A is on the bottom, C is on top. That's the law of superposition. And so older layers are on the bottom, younger layers are on the top, all right? So we would go A, B, C. That's our first section there. What's the next event that's happening? Now, we would look at fault D. Fault D cuts through layers A, B, and C. So we know A, B, and C are all older. They had to be there before the fault at D happened. D does not cut through E or go into F. And so we know that that fault is going to be it's going to be younger than A, B, and C, but it's going to be older than E and F. How do we know that? What principle did I just use? The law of cross-cutting relationships, right? Cross-cutting relationships is what we use when rocks cut through, a fault cuts through rocks or an intrusion cuts through rocks. Our other two events are the erosion event and the sedimentary layer on top. And so which one is older? Well, just based on superposition, we'd say F is, happening in layer C, that erosion event. and then E is on top, so E is going to be the youngest layer here. We can also use the chunks of C are in layer E. And so we could say, well, we know that E, because of the principle of inclusions, that E is younger than C because there are chunks of rock C inside of layer E. So we just used superposition, we used cross-cutting relationships and inclusions all to help us understand what's happening with these layers and sequence them. Let's do another one. Okay, so what do we see in this picture? I see a shale layer at C. I see B has a limestone layer, and A is a sandstone. We have an intrusion, an igneous intrusion, D, and we have fault E. So let's start out. What's my oldest event or layer here? We can see C is on the very bottom. So we know C is going to be the oldest layer, right? And then B, and then A. Those sedimentary layers are from youngest to oldest, oldest to youngest, CBA. And again, which law am I using there? I'm using the law of superposition, okay? Because C is on the bottom, A is on top. Now, I'm also kind of looking at this ahead of time and going, well, I see D and E are there, but what I know is that D and E both cross-cut through layers A, B, and C. So I know for sure that A, B, and C were all there before fault E or fault D occurred. Okay, so whoops, let's pause here. By cross-cutting relationships, I know that D and E are younger than A, B, and C. Now, how do I know which one came first? Which one's older, D or E? You can see that fault E cuts through layer D. That's why it's displaced. So fault D was there, intrusion D was there when fault E cut through it and caused it to be offset like that. So we know that E is younger than D. Fault E is the youngest event. The intrusion D would be the second youngest event. So if I was going in order from oldest to youngest, I would say layer C, layer B, layer A, intrusion D, and then fault E. That would be the sequence there. So I think those are the examples I have for you. Now you'll need to get some practice. And so I've provided a lot of extra opportunities, different layers for you to look at. Keep in mind, we've looked at superposition, cross-cutting, inclusions. You won't see a lot with fossil succession, but you will see some contact metamorphism and some original horizontality. So let's just remember, if we were to see along the edge of D here, if we were to see some hash marks or some kind of marking indicating that there's been a change in layer A around layer D, that then we could use contact metamorphism as a way to say D is younger than A. Likewise with original horizontality, if you ever see a rock layer that's tilted or folded, we know that that event happened after the rocks were already there. So the event that caused them to change happened later, is a younger event than the rocks actually forming. Okay, I think that's all for now. Good luck looking through those, and please don't hesitate to contact me with questions. Let's go, Ridge.